In this section we will cover both low voltage and high voltage tests. We will discuss the different types, what each test is evaluating, how to use both to minimize risks to the winding, and a basic understanding of which results pass, and which results do not pass. These understandings are necessary to optimize your motor testing program. We will be discussing static testing, which is when the motor is not operating, disconnected from the power source and locked out. It is important that anyone performing testing of motors understands and follows the lockout-tagout requirement of their facility as well as NFPA 70E safety guidelines. A static test program is designed to determine the health and reliability of the motor's insulation system while de-energized. We will be interrogating both the ground wall insulation integrity as well as the turn-to-turn insulation integrity. If your testing program does not interrogate both, you will miss issues. There are two classifications when we perform testing: low voltage and high voltage. Low voltage testing is measuring electrical parameters at or below nameplate bus voltages to determine a change in the electrical circuit's properties. Measuring, not stressing. High voltage testing is testing insulation at voltage levels similar to those the motor experiences to determine the integrity and reliability of the entire insulation system. The combination of low voltage and high voltage tests help us define the insulation condition with respect to its end of useful life. Let's look at the different type tests and what they are evaluating. Starting with low voltage tests. Resistance imbalance is measuring the actual resistance between phases. It's look for high resistance connections, improper internal connections and circuit shorting. Whether there is possible turns, coils or phases shorting together. Inductive imbalance is looking for winding imbalance due to improper connections or hard shorts. When a motor is wound, the inductive balance of the circuit can be helpful in validating the connections in the circuit. Also, if a motor has tripped, it can identify whether there is hard shorts between phases, coils or turns. It only indicates problems between windings if they have already occurred. Insulation resistance test evaluates the integrity of the ground wall insulation. It identifies degradation as well as effects that moisture or contamination have. Polarization index is a 10-minute IR test that determines the health of the insulation. It helps identify insulation embrittlement and degradation. The dielectric absorption test is like the pi test but lasting only 3 minutes long. It is used with smaller motors. The capacitance test identifies when contamination is building on the insulation. The result is trend over time. An increase in capacitance is a good indication that your winding is becoming contaminated with some type buildup. The step test is the first high voltage test that we will be performing. The step test is an insulation resistance test that increments the test voltage to a final target voltage level of, in our case, 2 times line voltage plus 1000. It can identify when the actual status of the insulation is near end of life as well as exposed conductors tracking to ground. Surge test is the only test that can evaluate the copper-to-copper insulation before failure. This test can identify weakness in the copper-to-copper insulation. To minimize risk to our motors and to establish effective predictive maintenance programs, we use a specific test sequence. The general idea is to perform the test sequence as a series of progressively more rigorous tests, accepting the idea that if a test fails, troubleshooting and repair should begin at that time. More rigorous testing should only commence after satisfactory diagnosis and/or repair. The test sequence when using the AWA test set is as follows. 1. Copper-to-copper resistance imbalance, 2. Insulation resistance, 3. Polarization index, 4. Dielectric absorption if a small motor, 4. High pot step voltage and 5. Surge. The test sequence when using the ADX test set is performed in groups. The first group is the RLC group, which includes inductance imbalance, impedance, copper-to-copper resistance imbalance, and capacitance if enabled. The DC group includes insulation resistance, polarization index, or dielectric absorption if a small motor, and the high-pot step voltage. The surge group includes the surge along with partial discharge on surge if enabled. Let's first discuss the RLC group. Possible discoveries while performing RLC testing include resistance copper-to-copper imbalance, high resistance, or open connections. Shorts turn-to-turn, coil-to-coil and phase-to-phase. Asymmetries in the magnetic circuit such as air gap, grounds, reversed coilsome group, or phases. Core damage, contamination. Resistance imbalance is performed with a DC source. Inductance is performed with an AC source at a set frequency. Inductance testing will and must be performed first in the test sequence. The ADX test leads and the AWA low voltage test leads are Kelvin leads. Kelvin leads are necessary to subtract lead resistance from the Totlo measurement. Kelvin leads use both sides of the connector. It is extremely important to accomplish a good connection on both sides to ensure a trustworthy result. Bad contact will result in invalid data. Inductive imbalance. Compare inductance between phases. Test is ran at 120 Hz and if enabled will be performed before any DC testing is performed. Inductive imbalance is used to interrogate windings for multiple grounds, shorts, misconnections, even incorrect wire size. First lead 1 to lead 2 is measured. Then lead 2 to lead 3 is measured. Then lead 1 to lead 3 is measured. Here we see issues with multiple grounds. Another issue with hard shorts between phases. Also, if the motor shop used different gauge wire between phases, or misconnected them, or possible rotor issues. Larger imbalances or phase angle difference may be the result of shorted, open, or misconnected coils or windings. We must be sure to reject results due to rotor rotating while testing, or issues from induced voltages. Resistance imbalance. Compare resistance between phases. Resistance imbalance is used to interrogate windings for differences due to loose connections, or possible hard phase-to-phase shorts or misconnections. First lead 1 to lead 2 is measured. Then lead 2 to lead 3 is measured. Then lead 1 to lead 3 is measured. Here we see issues with multiple grounds. Another issue with hard shorts between phases. Also, if the motor shop used different gauge wire between phases, or misconnections. The most common problem found with the resistance imbalance testing is loose connection. Typical problems found with resistance imbalance testing include hard shorts to motor core, Hard shorts between coils. Coils rewound with improper gauge wire. Loose or corroded connections, due to lug crimp or bolt hardware. When performing analysis for resistance imbalance results, consider these. Are reading near the test set limits? Greater than 900 ohm or less than 0.001 ohm. Confirm Kelvin lead connections are good. Swap leads and see if result follows. Reject issues from rotating rotor or induced voltages. And if severely out between all phases, this may be due to grounding. Inductance imbalance and resistance imbalance testing seem similar, so what are the differences? Resistance imbalance testing focuses on electrical continuity and uniformity of winding conductors, while inductance imbalance testing focuses on the magnetic characteristics and symmetry of the windings and rotor interaction. Both tests complement each other in motor diagnostics, with inductance imbalance testing typically revealing deeper winding or rotor faults not visible with resistance measurements. Capacitance testing measures the winding to ground capacitance. It is tested at 4000 Hz. It is recommended to perform this test at the motor rather than at the starter and through the long motor lines that are connecting the motor to the starter. If capacitance testing is enabled, the test set will prompt you to change the lead configuration prior to performing the test. Reconfiguring the test leads consists of using only leads 1 and 2. As seen here, the test set is prompting the user to disconnect lead 3 and the ground lead. Then move lead 2 to ground. While testing, keep lead 3 and the ground isolated from each other and ground. Capacitance of the winding to ground increases as contamination buildup occurs on the winding. Capacitance can be trended over time to determine whether the windings are becoming heavily contaminated. DC tests. Next we will discuss the DC group that include IR testing, pi testing, and high-pot step testing. The insulation resistance known as IR testing is measuring the resistance from the copper winding to ground. It is the resistance across the insulation. When IR testing, we apply rated voltage to the motor for 60 seconds. Our result is taken at the end of that 60 seconds. Does anyone know why we hold it for 60 seconds? If a low megohm result is measured, the motor could have insulation damage, allowing leakage current to flow through the insulation, or possibly copper parts such as connectors that are not sealed and allowing current to flow along the outside of the insulation. This is known as surface leakage. Typical problems include slot liner or enamel wire insulation burned or damaged. Motor might be full of dirt, pulp, water, or other contaminants. Contaminants create a path to ground either through the insulation or around it. Again, path around insulation is known as surface leakage. Surface leakage prevents us from knowing if the low megohm result is real insulation degradation or insulation that is being bypassed. IR testing is measuring the ground wall insulation. Ground being the actual stator core made up of laminations. As seen here, the insulation between the copper conductor and the core is the enamel coating surrounding the turn insulation and Nomex slot liner. In effect, we have a conductor on one side, a ground conductor on the other side, and insulating material in the middle. The insulation includes some free electrons as well as molecules known as dipoles. When DC voltage is applied across the insulator, the negative charged electrons in the insulation are attracted to the positive charged side, which is the conductor, and away from the negative charged side, which is the ground. Since an insulator does not have many free electrons, the time required for the electrons to flow is short. This flow of electrons is called the charge current. Normally within 60 seconds all the charge current is completed. This is why we hold the voltage for 60 seconds when performing the IR test. The graph is the charging current trend. Steep incline and then a slower decay. The polarization index test for larger motors and the dielectric absorption test for smaller motors is used to analyze the mechanical integrity of the insulation. Aged or thermally cycled insulation systems become hardened and brittle. Leakage current can be reviewed to determine contamination, moisture influences, deterioration. During the PI test, the voltage is held for 10 minutes. The 10-minute resistance reading is divided by the 1-minute resistance reading. The result is a ratio. The expectation for healthy insulation is for the resistance measurement to increase over time and at least double, which is a ratio of 2. The dielectric absorption test, performed on smaller motors, is a test where the voltage is held for 3 minutes. The 3-minute resistance reading is divided by the 30-second resistance reading. The result is a ratio. Some molecules, called dipoles, in the insulator are very polar. When an electric field is applied across the insulator, the polar molecules align themselves along the direction of the electric field. This current is called polarization current. It continues until all the polar molecules align themselves along the direction of electric field. It can take 10 minutes to align the polar molecules along electric field. It is important to understand the polar molecules that have been aligned will relax once the voltage is removed. However, to fully randomize the dipoles requires energizing the winding with AC current. There are 4 components that contribute to the total leakage current. They are capacitive charge, as seen during the IR test, the polarizing current, which is the alignment of the dipoles, surface leakage, which is current that is bypassing our insulation, and finally conduction current, which is the current flowing through the insulation. Conduction current is what we want to know. Here we will watch what happens during a polarization index test and see how each of the 4 components respond to the applied voltage across the insulator. When the voltage is first applied, all 4 components are active. Although few, the negatively charged, free electrons indicated by the minus signs, will start to move toward positive charge conductor. This is the capacitive charge current, which will complete within 60 seconds. At the same time, the dipoles, indicated here with the oblong-shaped objects, will begin aligning themselves with the positive conductor and the negative ground plane. This will require much longer, sometimes 10 minutes on larger motors. And at the same time, the electron flow that is bypassing the insulation will flow. This is called surface leakage and is indicated by the dots flowing in the yellow region. And finally, the conduction current, indicated by the dots flowing through the insulator, which is what is constantly flowing through the insulation. We can see the effects of each component in the leakage current trend on the left. Initially, the current plot includes all 4 components, with largest portion being the charging component. Next we see the charging current decay, and within 60 seconds, the charge current is fully decayed. During the entire test, the dipoles are aligning. The polarizing current will slowly decay until all dipoles are aligned. After dipole alignment is complete, we are left with conduction current and surface leakage current. If surface leakage current is large enough, it will mask what is truly passing through the insulation. That is why we must do all we can to prevent surface leakage issues. One way is to ensure all internal connections are sealed. Another way to minimize surface leakage is to eliminate the stub-type connections in a motor. This is a picture of a motor with stub connections. When possible during a rewind, we will ask the motor shop if they can convert these type connections to a horseshoe connection. We use the 3-minute DA test rather than the 10-minute PI test on motors 100 horsepower and below, or when the megohm result is 5000 megohm and above after 1 minute. Some newer insulation systems will polarize more quickly. For a good insulator, resistive leakage current is tiny. It is always desirable to have a polarization index result of 2 to 5. It is undesirable to have a polarization index result less than 1.5 unless the resistance measurement is 5000 megohm and above. We never accept a pi result less than 1. It is always necessary to study the leakage current trend. We will study some results next. This graph represents a good pi result and a healthy insulation system. As voltage is held on the winding, the megohms are climbing and the leakage current is dropping, indicating good dipole alignment is occurring. The 1-minute meg result was 13,000 megohm and the 10-minute meg result was 49,000 megohm. 13 into 49 is a ratio of 3.76, which is greater than 2. Moisture does not drive the insulation resistance down unless there is true insulation degradation or surface leakage. When the megohm result is affected by moisture, the insulation is compromised and the motor is installed in a critical application, we should consider replacing the motor. Moisture does cause leakage current oscillations due to the polar charge of water molecules moving back and forth. Movement of charge is also known as current flow. The presence of water also increases the effective surface area of the insulation relative to the ground plane. This causes the capacitance to increase. The Harry current is caused by the polar nature of water. That movement of charge, current flow, is not through the insulation. Instead, the movement of current is a result of the changing capacitive currents. Step test. The step test is used for predictive testing. It is performed at a voltage level that is typical to what the motor sees during operation. Remember previously when we discussed the voltage spikes of sometimes 4 times line voltage during starting and stopping. The tests are governed by IEEE as well as other standards like NEMA and ISA and IEC. We have adopted the test voltage recommendations of METR, which is 2 time line plus 1000. During the step test, the DC voltage is applied to all 3 phases of the winding, raised slowly to a pre-programmed voltage step level, and held for a predetermined time period. This is continued until the target test voltage is reached. If the leakage current increases are linear, the motor insulation is likely in good condition. If the leakage current increases are nonlinear, the motor insulation is likely not in good condition. This is a poor test result even if the tester passes the test. The test set will not trip or fail the test on a nonlinear leakage current result. We must recognize this and fail the test ourselves. If the difference in leakage current between steps doubles, the test should be stopped. This is a very poor test result. The test set will not trip offline due to a doubling in leakage current between steps. Our max target test voltage is 2 times line-to-line voltage plus 1000, which is recommendation from METR. When set up properly, the tester will trip at and above 1000 microamp leakage current, below 100 megohm to ground, and if the test set detects an arc, the tester doesn't trip, it will pass the motor, even if the leakage current is nonlinear. That is why we must monitor leakage current during and following the test. We have a role in determining whether the motor passed or not. The test failure criteria for the DC step test is as follows. Leakage current over current. Micro arc detected. Difference in leakage current between steps doubles. Nonlinear response. Erratic leakage current behavior. This is an actual test result of the Megger AWADC step test. The blue pen is voltage, red is leakage current, and green is a plot of each end of step points. It's this green pen that must be linear for an acceptable test result. These spikes in leakage current is the charging current and the additional polarization current that occurs with each step in voltage. Holding voltage each step for 60 seconds allows the charging current and polarization current time to decay, and we are left with the conductive current. Sometimes when step testing large motors with long motor lines, 60 seconds is not enough time to allow the current to fully decay. This is due to the large capacitance in the circuit. In cases like this we might have to increase the holding time slightly. As this test is performed, the person performing the test should calculate the difference between each step and make sure the difference is not increasing. Differences here are 0.5, 0.5, 0.4, 0.5, 0.5, and 0.5. This is an excellent result. This example test has a poor result. Even though the test set did not trip, the end of step leakage current trend was nonlinear, which as we know is an indication that the insulation is becoming unstable. As a matter of fact, while holding the last step voltage, the leakage current became very erratic. This insulation system was very close to failing. By the way, the test set passed this motor. As we said, we must decide whether the result was acceptable, and not rely solely on the test set tripping. Let's calculate the dip in leakage current between steps and see if we could have determined this was happening while the test was running. First, the MEC result is low compared with the last example we looked at. This step was 4, then 5.4, then 5, then 10, and finally 14.4. The difference at step 5 actually doubled, and for some reason the test was not stopped. So, the test should have been stopped after step 5 and not risk punching a hole in this motor's insulation. If we allow the puncture to occur, the dielectric strength of the ground wall insulation is less than before the test. So, we would have degraded it. So why take the risk of damaging a motor with high voltage testing? Here is why. This motor MEC after 1 minute 378 MΩ. How many of us would say we have a good motor with a 378 MΩ MEC result? It wasn't until the voltage reached 7,350 volts that the instability began. So just testing at rated voltage does not tell us the integrity of the insulation. If we never test motors to the potential that is seen when operating, the motor will fail without us knowing there is degradation, and we are very near end of life. Our goal is to identify motors that are near the end of life, that are in the nose of this curve in the predictive zone. How can we use the test result to help identify where we are on this life curve? First, a nonlinear response means we have a motor that is somewhere towards the right on the end of life curve. If the slope is severely nonlinear at full test voltage, it is closer to failure than if slope turns slightly nonlinear at full test voltage. What voltage did it start to turn nonlinear? Below full test voltage is worse than at full test voltage. A slope that turns nonlinear at 1000 volts is closer to the failure point than if the slope turns nonlinear at 2000 volts. And finally, did the motor trip on overcurrent or arc detect? If so, the motor dielectric is below the test voltage threshold. The step test is more than a go-no-go test. We must study the end of step trend for a linear result and the leakage current trend to see if there is an erratic indication, which can mean the insulation is trying to break down or something is allowing the insulation to be bypassed. When deciding follow-up action, review these. What voltage did the trend become nonlinear? A lower level is worse than higher level. How severe was the nonlinear result? How critical is this motor application? How much time is available to possibly replace the motor? Remember, a nonlinear result indicates we have a motor that is somewhere toward the right side of the end of life curve. When testing from the starter out to the motor, there are other components under test. In this example, we experienced an overcurrent trip at approximately 1780 volts while performing the high voltage step voltage test. The motor was disconnected at the motor wiring box and we then tested only the motor line. We again experienced an overcurrent trip at same voltage level 1780 volts. Upon close inspection, we identified the point at which the test voltage was arcing through one of the motor lines. It appeared to be occurring where the cable passes through the conduit bushing in the motor wiring box. The area was taped and the circuit was retested and passed. So, we cannot fail the motor when testing from the starter until we confirm it is the motor by disconnecting at the motor and retesting. When using splicing boots, and you remove them for some reason, I recommend replacing them with new ones rather than reusing the old ones. This is due to the possible contamination that can penetrate the boot each time it is reused. If contamination enters the inside of the boot, surface leakage can allow tracking and your step tests could fail. The IR, PI, and step tests interrogate ground wall insulation. But we know windings fail between turns, coils and phases as well as to ground. Let's review the different failure modes that are possible within a motor winding. With each, ask yourself, can ground wall testing alone interrogate this type of failure? And can it allow us to identify the weakness prior to failure? Or do we need something else in our predictive program? First, turn to ground. Can ground wall testing interrogate this weakness and fault condition? The answer is yes, it can. Next is turn to turn. Can ground wall testing interrogate this weakness and fault condition? The answer is no, it cannot. Next is coil to coil. Can ground wall testing interrogate this weakness and fault condition? The answer is no, it cannot. And finally is phase to phase. Can ground wall testing interrogate this weakness and fault condition? The answer is no, it cannot. A surge test can detect a fault between these as well as identify weakness in the turn-to-turn and phase-to-phase insulation. Remember, the resistance imbalance and inductive imbalance tests interrogate the turn insulation, however they do not find a weakness or fault unless a fault has already occurred. That is too late. We want to find turn insulation weakness prior to failing, when the motor is nearing end of life. Surge test. Surge testing is the only test that interrogates weakness of the turn insulation and can predict failure prior to failing. Surge testing has been around since 1936 and was first developed by General Electric and Westinghouse. The surge test simulates what the motor experiences when in service and starting and stopping. With the surge test, we are looking for something to change. What changes when coils short out is inductance of the winding. And that is what the surge test is looking for. An inductance change while pulsing the winding. Megger compares the surge test to hitting a bell with a hammer. If we hit the bell with a hammer, it will ring at a resonant frequency that is determined by its mass, stiffness, and resistance to oscillation. The ringing will start out loud and dissipate until it is no longer ringing. If we hit the bell harder, the tone would become louder, represented by the increase in amplitude of the waveform, but the frequency would be the same. If the bell had a crack and we hit the bell hard enough to cause the crack to close further, the stiffness changes, and therefore, change the resonant frequency of the ringing waveform. The frequency would increase, and the waveform would shift left. A surge test can detect a fault between turns by observing a jump in resonant frequency of the motor and tester inductance/capacitance circuit. The surge test consists of applying a fast rise time, high current impulse to a winding. This fast rise time impulse will induce a voltage difference between adjacent loops of wire within the winding. If the insulation between the loops of wire is damaged or somewhat weakened, and if the voltage difference between the wires is high enough, there will be an arc between the wires. This arc changes the inductance of the circuit. That is seen by a change in the resonant frequency and surge waveform as well as the EAR graph. The result is a low energy arc and a change in the EAR graph. Surge testing is the electrical equivalent of hitting the bell with the hammer. There is a large capacitor contained inside the test set. During a surge test, the capacitor discharges into the winding circuit. Current flow will produce a magnetic field in the coils of the winding. When this field collapses, it will produce a current flow back into the capacitor. The capacitor will convert this reversing current flow into an electrostatic energy field. When the electrostatic energy field collapses, it will produce a current flow back into the winding. This process would repeat until the amplitude of the waveform completely decays. The voltage induced onto the turns of the winding will result in a nonlinear voltage drop across the winding. This nonlinear characteristic is what stresses the turn-to-turn insulation during the test. There is more stress on the turns near the lead end of the winding. The electrical resonance frequency of the circuit is inversely proportional to the inductance and capacitance of the circuit. See equation. If weak insulation exists between turns, the differential voltage will short out a bit of the winding. This causes the overall inductance and resistance of the circuit to go down. When the inductance goes down, the frequency of the oscillation will increase, causing the waveform to shift to the left. This is an illustration of the ringing frequency that is developed when the current between the capacitor and the winding is ringing. The frequency is determined by the equation 1 divided by square root of the inductance times capacitance. The voltage of the initial pulse does not change the frequency of the waveform. As the voltage increases, the ringing frequency stays the same. If during the surge test, the turns of the winding arc together, the actual inductance of the circuit changes. Inductance will decrease. According to the equation, when inductance decreases, the resonant frequency will increase. This results in a shift to the left of the ringing waveform. The test will start out at 0 volts and with each pulse increase voltage slightly until full target voltage is accomplished. The test compares the waveforms between pulses to confirm the ring frequency hasn't shifted. The test set can compare the ring frequencies two ways, line to line or pulse to pulse. Line to line surge is comparing waveforms between phases. This requires the rotor removed from the stator due to the rotor influence between phases. A pulse-to-pulse test compares waveforms of the same phase as voltage is increased. This is test we perform in the mills because the rotor is installed. Rotor influence does not affect a pulse-to-pulse test result. A successful test is when the ringing frequency does not change throughout test. How does the tester know if the ringing frequency changes? The tester pulses the winding, waits for the ring frequency to decay and captures the area of the waveform. Then it raises voltage another 10 volts, captures the area of that waveform and compares area of the last waveform to the previous waveform. This is how it knows whether the waveform has or hasn't changed. It measures the area of the two waveforms that it's comparing, and if the error ratio of the area is above our trip threshold, the tester will trip. The only difference in area of the two waveforms that should be present is the slight increase in voltage. After each comparison, a point is plotted onto the ear graph. Reviewing the ear graph will confirm whether there are any differences between waveforms. If any plot is above the target trip threshold, the tester will trip offline. Here the trip threshold if 2% here. This is the EAR graph. After each search waveform area comparison, a point is plotted on this graph. The point represents the difference in area of the previous waveform and the last waveform. If any plot is above the target trip threshold, the tester will trip offline. Here the trip threshold is 2% EAR. As the test progresses, the pulse voltage increases, the area between waveforms is measured and the error area ratio is plotted on the EAR graph. Again the voltage is raised and areas compared, EAR plotted, and the test is continued. The comparisons continue until either we reach full target voltage or EAR plot exceeds our trip threshold. After reaching full target voltage on one phase, the tester will switch to the next phase and perform the same test beginning with low voltage. Here is a good surge EAR result. It should be noted that even if there are no pulses that exceed the trip threshold, any pulses on the EAR graph should be investigated to determine if they are real. This is an excellent result with no pulsing. The pulsing here has everything to do with an earlier version software revision. Latest software revision and Comp Mode 3 have corrected this issue. The IEEE standard for surge test voltages is IEEE 522. If new, they recommend testing at 3.5 per unit. In service motors, the recommendation is 75% of the new test voltage. We use the same voltage for both step testing and surge testing. The mega recommendation 2 timeline plus 1000. This table shows many different recommendations. IEEE 95 is the step test standard and IEEE 522 is the surge test standard. Surge test with partial discharge. Available with a DX model. Partial discharge in motors refers to a localized electrical breakdown within the motor insulation system, where only part of the insulation between conductors is bridged by the discharge rather than a complete breakdown. This phenomenon is a significant indicator of insulation deterioration and, if left unchecked, can lead to major failures and downtime in electric motors over time. Partial discharge typically occurs because of imperfections, voids, or contaminants in insulation materials, or due to high local electrical stress inside or on the surface of insulation. Internal PD takes place within the insulation, while surface PD happens when the surrounding air is ionized near the winding surface, potentially visible as ultraviolet light and tiny sparks. Over time, repetitive partial discharges erode the insulation, decreasing the lifespan of the motor. Effects of partial discharge. Degradation of winding insulation, increasing risk of motor failure. Reduced motor reliability due to brittle and weakened insulation. PD activity is often present before actual insulation failure, serving as an early warning for required maintenance. Causes and risk factors. Contaminants, voids, or poor manufacturing in insulation. Frequent voltage spikes, especially from modern drives, example frequency converters and PWM systems, which have fast rise/fall times and high repetitive rates. Environmental factors like moisture, temperature, and aging of insulation materials. How surge testing with partial discharge works. During surge testing, which applies high voltage pulses to motor windings, the presence of partial discharge is monitored by detecting high-frequency discharge activity that occurs in voids or imperfections in the insulation system. Surge testing applies controlled high-voltage surge pulses to motor windings to stress the insulation. Simultaneously, sensitive instruments equipped with partial discharge modules detect high-frequency emissions caused by PD activity in the insulation. The test identifies key parameters such as partial discharge inception voltage, PDIV. This is on voltage increase, the voltage at which PD activity first appears. Partial discharge extinction voltage, PDEV. This is on voltage decrease, the voltage at which PD activity ceases when voltage is ramped down. Repetitive partial discharge voltage, RPDIV. This is on voltage increase, the initial voltage where 50% of surge pulses contain PD. Repetitive partial discharge extinction voltage, RPDEV. This is on voltage decrease, the last voltage where 50% of surge pulses contain PD. To address noise, two thresholds are defined during testing. PD threshold, millivolts, the amplitude at which a PD event is counted towards the PD event. PD event limit, count, the cumulative number of PD events during each surge pulse required to constitute a PD surge pulse. During surge testing, the PD metrics are recorded and displayed if both the PD threshold and PD event limit are accomplished. As voltage increases, PDIV and RPDIV will be recorded if PD occurs. As voltage decreases, RPDEV and PDEV will be recorded if PD occurs. The house plot has different y-axis scales for the voltage magnitude and the number PD events. They share the x-axis, which is the surge pulse number. Any PD event, above the MV threshold, will show on the house plot, even if it does not meet event count limit. The PD events, above PD threshold, are not considered PD surge pulse unless the event count meets or exceeds the PD event limit. PD event limit is the cumulative number of PD events during each surge pulse required to constitute a PD surge pulse. During this test, the PD threshold setting, MV, is 4 and the PD event limit setting is 3. The plotted PD events did not meet the PD event limit, count, which are the cumulative number of PD events during each surge pulse required to constitute a PD surge pulse. PDIV and PDEV can be compared to line voltage, and the expected voltage spikes the asset may encounter in operation. The PD metrics can also be trended over time to determine if PD events are increasing or increasing at lower levels. Here are some examples. Which of these might be an issue with the motor reliability going forward? PDIV equals 1200 volts. PDEV equals 8000 volts. Bus volts equals 4160 volts. Conclusion: PD may occur during a voltage spike and will stop after the spike. PDIV equals 8000 volts. PDEV equals 3800 volts. Bus volts equals 4160 volts. Conclusion: PD may occur during a voltage spike and will not stop after the spike. PDIV equals 4000 volts. PDEV equals 1500 volts. Bus volts equals 4160 volts. Conclusion: PD may occur during normal operation and will continue while energized.